Yes, good morning everyone. In this section we are going to define two functions, Meromorphic function, entire function. These two functions are very important, but Meromorphic function we will discuss its detail in the later section. Right now only definition is required to understand, and then also we are going to do one theorem which is very important and expected one. So let's start. Meromorphic function. A function which has a poles as its only singularities in the finite part of the plane. Which means a function which has singularities only and only poles. Right? In the last section, in the last video, we have also done one theorem, that is your rational function has no singularity other than poles. Right? Also in the finite part of the plane. We have done the proof of this theorem in the last video, you can check. Then another definition, you can also say that a function which has no singularities other than poles in the finite part of the plane. So only and only singularities should be the poles, right? Such functions are meromorphic functions. Then is the entire function. A function which has no singularity in the finite part of the plane. That means no singularity, which means function is analytic, right? In the finite part of the plane. So example, e the power z, this is your entire function, but provided, just keep in mind, they are saying that there should be no singularity in the finite part of the plane. So all your trigonometry functions, polynomials, this e the power z, all are entire functions. That means all are analytic in the finite part of the plane. There are some remarks which are very important and also very useful in net entrance exams. So it's written that fz is analytic for mod z strictly greater than r, that means outside the circle. If and only if f of 1 by z, just replace z with 1 by z. F of 1 by z is analytic for 1 by z mod strictly less than 1 by r. Right? This is your remark. Hence, fz has an isolated singularity at z equal to infinity if and only if, again we have to replace, f of 1 by z has an isolated singularity at, what is 1 by infinity? This is 0. So if at infinity I am having function to be having isolated singularity, then f of 1 by z has an isolated singularity at z equal to 0. Right? Just you have to reciprocate. For example, a very good example is there. I'm having the function fz to be as z squared plus 1. It has a pole of order 2 at z equal to infinity. Why? Because if you check f of 1 by z, this is equal to 1 over z squared plus 1. Now this function has a pole of order 2 at z equal to 0. Right? If you put the denominator equal to 0, what is the power over here? This is 2. So f of 1 by z, if it is having the pole of order 2 at z equal to 0, you can say that fz has a pole of order 2 at z equal to infinity. Now we are going to start the theorem. A function which has no singularity in the finite part of the plane and at infinity is constant, right? So here there is a little concept that a function which has no singularity in the finite part of the plane, that means they are talking about the entire function, but they are also saying that this function should also have no singularity at infinity. If in both the cases the function is having no singularity nowhere, not in the finite part of the plane, also not at infinity, then such function is constant function, right? So let's start with the proof. Now since the function fz, let's take our function to be fz, it has no singularity in the finite part of the plane. No singularity means this function is analytic in the finite part of the plane, and the function which are analytic, they can be expanded in the Taylor form. So it can be expanded in the Taylor series in any circle, say mod z equal to r, where r is large, right? So I'm writing this function as this is equal to, sorry, I need to change the color of the pen. So this is equal to summation n going from 0 to infinity. As in the Taylor series, I'm expanding this. So this is a n z the power n. Mark this as 1, right? Now again, fz has no singularity at infinity, which means fz has no singularity at z equal to infinity, which means right now we have just read the remark. Can I say f of 1 by z is analytic at z equal to 0? See, f of z has no singularity at z equal to infinity. F of 1 by z has no singularity at z equal to 0. No singularity means function is analytic. So f of 1 by z is analytic at z equal to 0. Clear? Alright. I'm writing a step in between so that it's more clear to you. Alright, fz has no singularity at z equal to infinity. Okay, so f of 1 by z has no singularity at z equal to 0. Now can I say that f of 1 by z is analytic because it is having no singularity at z equal to 0. Alright, now it's clear to you. Okay, now further, since fz has no singularity in the finite part of the plane, so f of 1 by z also cannot have singularity in the finite part of the plane. So we expand. Now because this f of 1 by z is analytic at z equal to 0, now because this is analytic, I'm expanding again in the Taylor series. So we expand f of 1 by z by Taylor's theorem. F of 1 by z can be written as summation n going from 0 to infinity. Let's take now the constant as the coefficient as bn, z the power n. Mark this as 2. In the first, we have written fz to be in the Taylor form, having the coefficient an, and then I have written f of 1 by z to be in the Taylor's theorem, Taylor form, having the coefficient as bn, right? Mark this as 2. Now because I'm having f of 1 by z over here, so from 1 I have to replace this z with 1 by z so that I can equate both these two equations, right? So in the next step I'm going to replace z with 1 by z, and I'm getting here as 1 over z the power n. So replacing z by 1 by z in 1, we have f of 1 by z is equal to summation n going from 0 to infinity an over z the power n. Mark this as 3. Now from 2 and 3, what is 2? I'm also having here f of 1 by z. Let's equate these two. F of 1 by z is equal to summation n 0 to infinity bn z the power n is also equal to this summation n going from 0 to infinity an over z the power n, or you can also write it as z the power minus n. I'm taking z the power n in the numerator as z the power minus n. Mark this as 4. Now when can this be equal? What is the condition so that these two are equal? Now 4 can hold only if this bn coefficient and an coefficient should be 0. for n 1, 2, 3, for all these natural numbers, right? And if n is not natural number, let's say n equal to 0, I'm having b0 is equal to a0, b0 is equal to a0, right? So it follows that this function f of z is equal to a0 is equal to b0 is equal to constant. You can this a0 and b0 can be any constant, right? So finally it has been proved that is a function which has no singularity in the finite part of the plane or at infinity is constant function, right? Okay, thank you. Next time we will be doing the exercises based on these theorems. Hope it's very clear to you. You just have to revise all the definitions and remarks for the next video for examples and other concepts. So let's meet in the next video. Alright, goodbye. Have a very nice day.